Hey guys, it's Chili here. Welcome back to Intermediate C++ Tutorial 23. Today we're talking about bit manipulation with bitwise operators. It's going to let us pack our fudge, and it is going to let us flip our flags. I didn't say what you thought I said. Not that there's anything wrong with that. Let's get started. So, bitwise manipulation, obviously you're going to be working in binary. So the first thing is, you've got to be able to understand binary representations. Now, I've already explained this. I've taught this in Intermediate Video 1. And there's also about 1 billion videos on this on the internet, so I'm not going to go over it again here. You're expected to understand how to read binary. Now, the other thing is we're going to want to be able to output the binary on the screen, a binary representation. Now, IOStream gives us a way of outputting in hexadecimal, in decimal, of course, also in octal, but not in binary. Thank you very much, standard library. So I've written my own function here. It will convert an unsigned int. It'll give you the representation of that in binary as a string. It also lets you set a minimum number of digits for that. And now the other thing that I want to talk about here is C++ gives us different ways of representing our literal values. So we can represent as a decimal, we can represent as hexadecimal, or we can represent now as binary as of C++ 11. But as you can see here, the IDE tells us these are all actually the same value. And if we run the program and output them as binary, we can see they all give us the same bit patterns. So this is what we're going to be using to explore the different bitwise operators. Let's get started. All right, so the first operation we're looking at is the bitwise AND. We've got two ints, A and B. We're going to output A, we're going to output B, and then we're going to output the result of the bitwise AND of A and B. And I'm doing those all in binary representation. If we run this, we're going to see A, B, those are the ones we set. And here is the result A and B. And it's very simple. It's just the logical AND, the Boolean AND between bits. So for every bit, it'll check both bits, see if they're both set. If they are both set, it sets it to 1, otherwise it sets it to 0. And it does that for every single bit in these two 32-bit numbers, and it sets the corresponding bit in the result. So here you can see the only places where the result is being set is where they're both 1, all other places are set to 0. That is the bitwise AND, very simple. Now, that's one way of looking at it. The other way that we often look at it as is a mask. So when you look at it as a mask, the places where, in B, the places where the 1 is set, A will fall through. So here we're getting the value of A, wherever B was set to 1. When we set B to 0 here, what we're doing is we're masking out that part of A. So here, no matter what A is, it's going to be cleared all to 0. So using these ones, we can set little windows where A's value can fall through into the result. And the zeros are places where it's masked out and it cannot penetrate through into the result. That is the other way of looking at bitwise operators, and this is actually the most common way that I think about them when I'm using them, in terms of masking like this. So you can use ones to select the parts of A that will make it through to the result. And the same sort of concept applies to bitwise OR. So you do a bitwise OR with the single pipe here, just like you use the single ampersand for bitwise AND. And yeah, when you run this, you'll see that it just goes through every bit, and as long as one of the two operands is set, the result is going to be, the corresponding bit in the result is also going to be set. So the only time it's 0 is if both A and B, their corresponding bit is also 0. And that's one way of looking at it. Now, the other way of looking at bitwise OR is you can think of it as mashing two packed values together. So let's say in A, the top 4 bits are set to 0, the bottom 4 bits are set to some value. And in B, the top 4 bits are set to some value, and the bottom 4 bits are set to 0. And you can mash these two together with an OR. But you see here, because the top bits were set to 0, it's not displaying the full 8 bits. So what I can do here is I can make it, I can force it to display 8 bits, like this. Now, if I run it, there you go. So you see here that now we've mashed the bottom 4 bits of A and the top 4 bits of B together to form a packed 8-bit value here. And that is another way of looking at the bitwise OR. Now, the next most important operation, in my opinion, is the shifting operations, and they are very simple. So the shift is performed with this operation here, the two angle braces pointing to the left. Now, you probably recognize this as the insertion operator for streams, but that is an overload. The original meaning of this operator is to shift bits to the left. So if we shift 4 to the left, A's bits, we shift them 4 to the left. It is, I think you can predict what it's going to look like. Yeah, this bit pattern here has just been shifted over by 4 binary places. And now that bit pattern appears over here. Same idea for shift right. So if I take this bit pattern and I shift it right by 4 bits, what we get is we get that bit pattern shifted over by 4 bits. With the shift left, it shifts in zeros in here, right? With the shift right, it shifts in zeros in here, except, and here's a tricky thing, there is one situation where it will not do that. So let's take a look at, we're going to set A to -1. So if we set A to -1, it is going to be, the bits are going to be all ones. That's FFFF in hexadecimal. You'll see that when I print this out. And then let's shift it right by 4 bits and see what happens. All ones, and after shifting right by 4, still all ones. So it does not shift in zeros in the top in this case. And the reason why is, well, basically, if it's a negative number, it is going to shift in ones when you shift to the right. That's the rule. If it is a positive number or an unsigned number, it's going to shift in zeros when you shift to the right. And it always shifts in zeros when you shift to the left. Now, here's some of you guys out there, you're saying, well, Chili, that is, that's interesting, that's cool, story bro, but, where's the payoff? This just seems like a bunch of bullshit. Why would I ever want to do this? Well, let's take a look at a little situation here. Let's say you've got 4 8-bit values here. These are 4 8-bit values. And we'll call them A, B, C, and D. And you want to pack them into a single 32-bit value for reasons. I don't know why. It doesn't matter. But you want to pack them all into a single 32-bit value. How do you do that? Well, what you can do is you can take these 8-bit values and you can shift them. So you can shift them over to their correct positions. And then you can use logical OR to mash them all together and form one 32-bit packed value, where all these 8-bit values are packed together in a single int. So in code, that's going to look something like this. We've got our 4 byte values, unsigned car. We're going to output them to start off with. And then we're going to have our result int that has them all packed together. And what we're going to do is, well, to put the first one, to put A in there, all we really need to do is just put the diagram backwards. I wanted A to be in the lowest order byte and D to be in the highest order byte, but you get the idea. So A is just going to be assigned to this 32-bit value because it's already in the correct place and there's nothing else to mash it in together with. So we can just do a simple assignment and set A, and then A will be in its correct place in the packed value. Now for B, we've got to shift it over by 8 bits. And so we show what B would look like shifted over by 8. And then what we do is we take the packed value, which currently contains A, and we OR it together with the shifted B. And that will give us XXBA. And then we do the same for C, and then for D. And then we have all of the 4 byte values packed into our single 32-bit int. Pack it up, pack it in, let me begin. We run this, we can see what's going on here a lot easier. So we got A, B, C, D, and we got our freaking, there we go. So here is after we have put A into the 32-bit int. It's right here, we just had to assign it. It was already in the correct place. Now B, when it's shifted over by 8, will look like this. And when we mash it together with our currently packed value, we will get this result, the A and B mashed together. And then with C, we shift it over by 16. It's now looking like this. We mash that together with this guy, and we get these 24 bits here all mashed together. We shift D over by 24. we mash it together with the other stuff we have accumulated, and we get the final packed value. And here we have these 4 bytes all packed into this 32-bit value. So that's great. We can pack these values all together into a 32-bit, but generally when you pack values together like this, at some point in the future, you're going to want to unpack them and, inspect and work with the individual values. How do you do that? Well, let's say we want to unpack C, right? What we'd have to do is we'd have to isolate C, first of all. So what we can do is we can mask out D, B, and A using an AND to mask them out. And then once we've gotten rid of them, all we got to do is shift C back into its base position. And there we go. We'd have the value of C. So how do we do that? Well, it's quite simple. I'm not gonna show all the steps. In short, what we want to do is we want to take the packed value and we want to mask out all of the other bits that we don't want. So the mask is going to be 1, 2, 3, 4, 5, 6, 7, 8. That's for C. And then 0, 0, 0, 0, 0, 0, 0, 0. That's for B. 0, 0, 0, 0, 0, 0, 0, 0. That's for A. You don't have to write the leading zeros. They don't really matter. So we mask to isolate the value that we want. And then we want to shift right by, I believe, 16. And that will get our value back into base position. And we can output that. We don't want to output it as binary though. Let's output it as an actual value, because we want to verify that it is the value that we chose. We should probably put brackets around this to not confuse our things. There we go. So this should output, what is C? C is 169. So we should get a 169 at the end here. And indeed we do get 169. That is C unpacked from our packed value. So to pack things up, pack them together, you're going to shift and OR. To unpack, you're going to AND and shift. And if you want to see a practical application for this technique, you need to look no further than the framework. The color class that we've been using so much, it stores the color as a single unsigned int. But of course, we know color is made up of RGB and one extra value, optional. And those are stored in the single unsigned int by packing the 8-bit values together. So we can see here the constructor for color here. It's got XRGB, and the way it does it is it just shifts the individual values or the individual components into place and mashes them all together with the bitwise OR operator, just like I showed you. And to get the individual channel values later on, all we're doing is again shifting and masking with AND. Here I'm doing the shifting first and then the masking afterwards. It's the same idea. You can mask first and shift. You can shift first and mask. The end result is going to be the same, it's just a little different form. A couple of things to note before we move on. First of all, here you can see I'm accumulating A, B, C, and D one after another in the packed value in separate operations. But in general, you'd probably just do that all in a single operation like this. Not a big deal either way. Now another thing is that you can actually shorten this syntax here. You can do packed or equals D, and this is the same thing, the same idea as with addition and subtraction. You can put the assignment together with the bitwise operation. This operation also works for shifting. You can see I'm using it here in 2bin. I'm using it right here, shifting to the right and assigning. So that's one thing. The other thing is this is very long. I would normally just do it like this, FF0000. So you can see, again, hexadecimal shorthand for binary. So I often use hexadecimal, especially when you've got very long numbers. Oh, but if you're going to do hexadecimal, you should probably make this an X, obviously. There we go. That's a little better. We can see here, even with these changes, the result is going to be the same. Same shit, different pile, right? All right, another very important application of bit manipulation is to pack flag values into a single int parameter that you can pass to a function. So you can pass a bunch of options to a function as a single value. And this is often used in things like the Windows API and DirectX. It's also used in a couple places in the standard library, so you need to know how to do it. So the basic idea is you have a bunch of options, and they're just integer values. But the important part about these integer values, they're just constant values really. The important part is that the values are all have a single bit set in their binary representations, and the different bits don't collide with each other. So none of the options, each option will have its own separate bit that is devoted to it. And the reason for this is now you can combine these different options together using the bitwise OR, and they won't collide with each other, and every unique combination of options will create a unique bit pattern. Then in the function that consumes the options, all you got to do is, if you want to check for a particular option, you just mask against that option, and if the result is 0, that means that that option wasn't set. But if the result is non-zero, then this will convert to a Boolean true, and then you will process according to the option being set. So we can do it like this. We can go stdcl, we'll do option to string, and we'll combine a couple of options together here. We'll combine the option kappa with porn, and if we run that, we get kappa porn. Beautiful. And you can add as many options into here as you like, and you will get those in the output result. And yeah, this doesn't seem super useful in this example here, but like I said, look in the framework, you look at something like main-window.cpp, and you'll see here when I'm calling Windows functions like adjust window rect, I've got different options in here. I've got the option Windows style caption, Windows style minimize box, Windows style system menu, and they're all being combined with bitwise OR. Same here. So you combine options with bitwise OR, and you can check for options with bitwise AND. Let's take a look at a couple of advanced operations that you can do. There are a couple more bitwise operators that we don't use as often. One of them is the bitwise NOT, and it just flips all the bits of the operand. It's a unary operator, it only works on one operand, and it just flips all the bits. So it looks like this. You run it, see all the bits got flipped. Sweet. So what can this be used for? Well, you can use this to erase one option from a big combination of options. So let's say we've got the options and we've got kappa, porn, and Ebola in there, and we want to remove just porn, leaving kappa and Ebola. So what we can do, or let's say we don't even know what options are in here, but all we want to do is we want to make sure that porn is not set, okay? So what I'm doing here is I'm going to output options. I'm going to output what porn is. I'm going to output the inverse of porn, or the complement of porn. And then I'm going to mask with the complement of porn. And what you can see here is, so here's my 3 options set. Here is the porn option. Here is the inverse of the porn. It has all 1s and only 0 where porn option is. And if I mask this with the complement of porn, it's going to clear only this bit, allow these other bits to fall through, and there you go. I've got kappa Ebola. I just erased porn from my options. So that's how you can erase a single option, is by mask anding with the complement of the option you want to erase. Now the last bitwise operator we're going to look at is exclusive OR. And the way exclusive OR works is like OR, if one of them are set, the result will be 1. And like OR, if they're both 0, the result will be 0. But unlike OR, if both are set, the result is 0. So exclusive OR is only true if A and B are different. If A and B are the same, it's false. That's the basic idea. Now the way you can use exclusive OR, you can think of it like I just told you, or you can think of it as a configurable complementer, or a configurable notter, flipper, if you will. So when it's 0, the result, when B is 0, the result is just going to be whatever A is. But when B is 1, the result is going to be the flip of A. So here, where B is all 1s, we're flipping A. And where B is all 0s, we're just taking A as it is. So you can, it's a variable flipper, configurable flipper, if you will, or toggler. So for example, we've got our options here, and we can toggle a couple of options. So let's toggle kappa and toggle memes. And when we do that, we see that result is now we have porn, memes, and Ebola. And that's pretty much all the operators there, and, or, shift, not, and exclusive OR. Now, an important thing I need to mention here is, well, let's say you've got 2 integer values here, these binary values, and you do if A and B. Well, what this does, this logical AND, is it's going to convert this A and B to Boolean. So if they're not 0, they'll be true. And they're both not 0, so this will be true. This whole thing will resolve to true, and we'll say, got him. Well, it should. Yeah, there we go. Now, what you sometimes see people doing is inside of an if statement, you'll see them using the bitwise AND or the bitwise OR as a logical AND or a logical OR. Now, this is actually not a very good idea because watch this. Fucked him. You see, this one does not resolve to the same thing as the logical AND. You get different results. And the reason why is, I mean, obviously, let me just put a 0 in here. You AND these two things together, you're going to get 0, the bitwise AND. Of course, if you convert A to Boolean and you convert B to Boolean, and then you take the logical or the logical AND of them, then you are going to get true. So don't use bitwise AND for a logical AND operation. That's dumb. Don't do it. Now there is one situation where you might want to do this, and the thing is with the logical AND, it does something called short circuiting. So if A is false, no matter what B is, the whole thing is going to resolve to false. So it doesn't even bother checking B. And if B is a function call, it doesn't call B. It short circuits B if A is false. Same thing with logical OR. If A is true, it doesn't matter what B is, so B is never evaluated. Now, if you want to avoid that short circuiting for whatever reason, then you might look into doing a logical, or not a logical, a bitwise or a bitwise AND. But remember, in this case, if your bits don't line up for whatever reason, you're not going to get the result that you expect. So you might want to first convert to bool and then do your bitwise AND, because converting to bool will, if it's non-zero, it'll convert to just a 1. So then the bits will all be in the right place, and when you do the bitwise operation, you'll get the expected result. But in general, if you're doing a logical operation for an if statement, use the logical operator. If you're doing a bitwise operation for bit banging stuff, use the bitwise. Now, the last thing we're going to talk about here is bitwise operators for optimization of arithmetic operations. So let's say we got A, we're going to shift it right by 1 bit, and we're going to output it as an integer. What's that going to look like? It's going to give us 12. Okay, so you shift the bits by right by 1 bit, it went from 24 to 12. If you do it by 2 bits, you're going to get 6, which is half of 12, which is half of 24. You get the pattern? Every bit that you shift right by divides by 2. So you can divide by powers of 2 by using shifting. And the same thing moving to the left, you can multiply by powers of 2 using shifting. And this optimization is often used because shifting is much faster than dividing. So if you're dividing by powers of 2 or multiplying by powers of 2, you can use shifting instead, and it's much faster. Now, here is the thing about that. Because you'll see a lot of people writing this code in, like, you know, I don't know, like coding competitions or whatever, and they're thinking they're making their code real fast. They're super smart. But here's the thing. So what I'm going to do is I'm going to get an input from the user, and then I am going to output that input divided by 4. The reason why I get an input from the user is because I'm going to run this in release mode, and if I just set A equal to some value, it is going to optimize out the whole calculation, just give me the result. The result, it can find it at compile time. So what I should do is I should put a breakpoint right here and run this again. Let's give it a number. Let's give it 24. And now we've broken. Let's go to the disassembly, and we can see here. Here is where it's doing the division. Shift arithmetic right. It's shifting right by 2 bits. And this is how it calculates the division by 4 instead of, you know, calling the division or using the division instruction, which is much, much slower. Division is very slow. Shifting right is incredibly fast. So the moral of the story is you don't need to do this, okay? So don't do this in your code if you just want an optimization, because the compiler is going to do that for you anyways. And basically, you're just making yourself look silly to people who know better. So don't do that. Use bit shifting if you are actually doing some kind of bit manipulation stuff, packing stuff, working with flags, I don't know, whatever. But if you're just going for arithmetic optimizations, don't worry, bro. The compiler is going to do that for you. So all you're doing is you're making your code more difficult to read, and you're making yourself look silly. But it is good to be aware of this bitwise optimization, because if you're aware of it, you can make choices in your design that that lead to faster code. So if you have the choice between dividing by 255 and dividing by 256, choose 256 because the compiler will make that super fast. Dividing by 255 will be super slow. Same idea applies for modulus. So if I do take some input and do mod 16 on that, let's put a breakpoint here, run that, input some dumb value, and we'll go to the disassembly. You will see here, here it is, and F. So mod 16 turns into a bitwise AND with 0F hexadecimal. See if you can figure out why that is. That's another little puzzle for you. Puzzle number 1, figure out how this code works. It's not that difficult. Puzzle number 2, figure out why mod 16 turns into bitwise AND with F. But that's going to about do it for today. This bitwise stuff, you don't use it that often. It mostly just makes your code more confusing and makes you look like an edgelord. But sometimes you do need to use it when you're working with functions that take parameters that are packed together, flags, or when you're working with packed values like colors, then you do need to use bitwise. And so there you go. Here it is. I hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more C++.